Type 1 and type 2 errors. I have a couple questions for you. Do you think that an innocent person has ever been wrongly accused and gone to jail?
No, it's never happened.
That happens. Do you think that a guilty person has ever been considered not guilty and let back into the world?
Yeah.
O.J. Simpson, right? No, I'm kidding. Yeah, it happens. But wait, why does that happen? If a guilty person is sitting there, why would the jury say that they're not guilty? Because the evidence wasn't convincing enough. It did not pass that threshold of convincing, right? That is exactly what we are doing in stats as well. Sometimes we screw up. It just is what it is. So we have two types of errors. We have a type 1 and a type 2. Those are Roman numerals, by the way. Type 1. This is when we reject the null hypothesis, but should not have. In that situation, we said the evidence was convincing, but the null hypothesis was actually true. Now, I know that sounds like I just said that we should have accepted the null hypothesis, but that's not true, okay? We don't accept a hoe, right? Okay. Think about a trial again. So, you are innocent until proven guilty, okay? The jury comes back and says that you're either guilty or not guilty based on the amount of evidence that they have. They never say that you are in fact innocent. But think about that person. In real life, that person either is innocent or guilty, right? But the jury doesn't get to say that they are innocent. They only get to say if they're guilty based on the evidence. But in real life, they really are either guilty or innocent, okay? Our null hypothesis is either true or not in real life, but we're just looking for evidence of an alternative. And we either get that evidence or we don't, okay? All right, that's a type 1. Type 2. Type 2. A type 2 error is when we fail, watch this, fail to reject the null hypothesis. Why did I write it like that? This is to help you remember which one of the errors can happen in which situation. We fail to reject the null hypothesis, but should have rejected. In this situation, we did not say that the person was guilty, but they really were. Okay? In this situation, we did not reject the null. I'm sorry, I said that backwards. In this situation, we did not reject the innocence, the null hypothesis, but we should have rejected the innocence. Okay? This situation, we said the evidence was not convincing enough but the alternative was actually true. Now, one thing to point out. You can only make a type 1 error when you have rejected the null hypothesis. It's literally the definition of a type 1 error. A type 1 error is when you have rejected the null hypothesis, but you shouldn't have. You can only make a type 2 error if you have failed to reject the null hypothesis. You cannot make a type 2 error when you have rejected the null hypothesis. It's part of the definition, okay? So that's why if you write it this way, fail to reject, that can remind you that that can only be a type 2 error. Cool, cool? Cool. All right. Let's look at some examples. Oh, actually, no. Here's a really cool little chart. In actuality, either the null hypothesis is true or the alternative is true. Again, the person sitting in the courtroom is either innocent or guilty, okay? But our decision, based on the evidence that we have, is that we're either going to reject the null hypothesis or we're going to fail to reject the null hypothesis. Is this giving y'all Punnett Square vibes? Yes. I'm sorry. Okay, now we need to kind of think about what's happening here. If in all actuality the null hypothesis really is true and we reject it, what has happened here? What kind of error has happened? That's the type 1 error. Now, I have some breaking news for you. The probability that we make a type 1 error is equal to the significance level. So when we have a significance level of 5%, that means we have a 5% chance of rejecting the null hypothesis when we should not have done that. Okay? 5% is our main alpha that we use. All right, let's think about this for a second. We have rejected the null hypothesis in favor of the alternative. And the alternative is true. What has happened here? Nope. Nope.
You're right.
Very good. We have rejected the null hypothesis in favor of the true alternative. We have done a good job, folks. We have sent a guilty person to jail. Let's go. What if we fail to reject the null hypothesis? We do not reject it. And the null hypothesis is true. What have we done? Nope.
No, you're right.
You did a good job. Again. This is when we say that the person is not guilty and they truly are innocent. We just let an innocent person go free. Good job. But what if we fail to reject the null hypothesis, but the alternative was what was true?
Type 2.
That's a type 2. In this situation, we said they weren't guilty, and they murdered the person. Sad, right? All right. This is where OJ lives. So, type 2 error goes right there. What questions do you guys have about that chart? That's just to help you put it all together.
Does the probability of type 2 equal anything?
I'm so glad you asked that, Lexi. Lexi said, does the probability of a type 2 equal anything? It sure does. Anybody want to guess what it equals? Nope.
0.
You would think it's 1 minus alpha, but it's not.
Alpha minus 1.
It's not alpha minus 1.
It's an interactive paper.
0.
It's not 0.
Infinity. 1.
It's not 1. It is
Alpha.
beta. So, do any of you know the Greek alphabet? What's the first letter of the Greek alphabet? So the probability of type 1 error is alpha. That's the first letter of the Greek alphabet. The probability of a type 2 error is beta.
Can my friends come in?
I'll be quiet. The probability of a type 2 error is beta. Beta is the second letter of a Greek alphabet.
I have to pee so bad. This
Let's look at an example. All right, kids, back to the speeding example, okay? Officer Tranum wants to determine if it's worth the cost to install speed sensor and traffic camera at the entrance of McKinney Boyd High School. McKinney PD will get the cameras if we can prove that the true proportion is less. Okay, check this out. The significance level is 5%. Significance level is 5%. We need to describe a type 1 and a type 2 error and the consequence of each. Type 1, that is when we reject the null hypothesis, but should not have. Okay, what does that mean in context of this problem? That means that we said there is convincing evidence that P is greater than 0.2, but it really isn't. Oh no! Hayden, what happens here?
It's a hoe.
If we say that the true proportion is greater than 20% and we find convincing evidence of that, what's going to happen with the speed sensors? Are we going to get them?
Let me consult my notes.
If we say we have convincing evidence that P is greater than 0.2, do we get the speed sensors and the traffic cameras?
No.
No.
Yes. Yes, we do. Yes.
Ladies and gentlemen, listen.
Yes.
If we say that we have convincing evidence that P is greater than 0.2, do we get the speed sensor and traffic cameras?
Yes.
Yes, but
Let's go. Doesn't look right.
that was the wrong decision. So what's the consequence here? We get the speed sensors and traffic cameras, but did we need them?
No.
No, we didn't. So we have wasted McKinney PD money.
Good.
It's tragic. So the consequence is we get unneeded cameras and sensors. We have wasted money. This is not good. This is bad. By the way, what's the probability that that has happened?
20%.
Nope.
Alpha.
Alpha, which is 0.05. The probability that we have wasted McKinney PD money is 5%. Okay. Type 2. That is when we fail to reject the null hypothesis, but should have rejected. Okay, so what happens in this situation? In this situation, we said there is not convincing evidence that P is greater than 0.2. We say that there's not convincing evidence that we have a speeding problem, but there is a problem. And what's the consequence of this one? If we fail to reject the null hypothesis, are we going to get the speed cameras?
No.
Nope. We are not going to get the speed cameras. But are they needed?
Yeah. Yes.
Yes. So what's the consequence here?
Undocumented speeding.
We don't get the speed cameras. We don't get the sensors. We have speeding continue. Freshmen are getting hit and killed every day. It's just terrible.
That's a little too real, Miss Lakey.
Isn't this a bad, bad, bad thing? Just saying. So,
I mean, it already happened, just like
the consequence is an unsafe environment. Was that? Should I maybe not have said that?
Oh, no, it's funny.
Okay. All right. Cool. All right. So here's my question to you: which one of these is worse? Is it worse that we waste the money and get unneeded sensors, or is it worse that we have possible death?
Death.
Obviously, that's worse, right? So we would want to minimize this chance of happening. Yes, ma'am. Consequence? The consequence of it happening? Consequence of it happening? Wait, where? Oh, convincing evidence. I'm sorry. That one is convincing evidence. All right, cool.
Wait.
All right, here we go.
My physics teacher last year.
Sorry, I was in a waiting room for like an hour and a half. And then I was just about to get in my phone now.
No way.
All right.
No way.
The probability. I've already said this once, so we're just going to write it really fast. Here it is, kids. Write it down. The probability of a type 1 error is equal to the significance level. You got it? Write it down. Come on. The probability of a type 1 error is equal to the significance level. You got it? What letter of the Greek alphabet is alpha? The first one, type 1 error. The probability of type 1 error is alpha. You see that? You see how that goes together? Okay, cool. Ahem. In the previous example, we were testing the following hypothesis where P is the true proportion of all cars to speed in the school zone. Suppose that the police commissioner decided to carry out his own test using a random sample of 250 cars and a significance level of alpha equals 0.1. What is the probability that the police commissioner makes a type 1 error?
10%.
10%, 0.1. Ladies and gentlemen, if you miss that on the test, probability of a type 1 error is equal to alpha, which is literally given to you in the problem. 10 or 10%. 0.10 or 10%. Those should be the kind of questions on the test that you get right no matter what. Right? Right.
You should put more than one of those points on.
Yeah, that was actually crazy though. Giving cash.
Last questions.
Instead of the shorts, you put a green.
All right. Hayden, stop. Hayden.
Unsafe environment.
Very. The manager of a fast food restaurant wants to reduce the proportion of drive-through customers. Shh. 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 The manager of a fast food restaurant wants to reduce the proportion of drive-through customers who have to wait longer than 2 minutes to receive their food after placing an order. Based on store records, the proportion of customers who had to wait longer than 2 minutes was P equals 0.63. That's what is happening. That is the status quo. To reduce this proportion, the manager assigns an additional employee to the drive-through orders. During the next month, the manager collects a random sample of 250 drive-through times and finds that the new P hat is 0.576. Ladies and gentlemen, did the proportion of customers that had to wait longer than 2 minutes go down?
Yes.
Does it look like this person made a difference?
Yes.
But did they really, or was that sampling variability? Hence why we do the whole rest of the problem. All right, we have alpha, a significance level of 0.1. Our null hypothesis is that the true proportion continues to be the status quo. The alternative is that the true proportion is less than 63%, and therefore, they did good. The p-value, the p-value is 0.0385. We need to interpret this. Assuming the true proportion has been 0.63. There is a 0.0385, basically a 3.85% chance that our sample is 0.576 or less due to sampling variability. Assuming that the true proportion has been 63%, there's basically a 4% chance that our sample was sampling variability. That means that there's basically a 96% chance. That means that there's basically a 96% chance that there was actual difference made. Okay? Now, the threshold for convincing evidence is 0.1 or 10%. So let's see. That's the last part. We'll get there in a second. Actually, we're going to just skip down and do that right now. Part C. This is part C. Everybody, we are on part C. We skipped part B for a second. Do you got me? The p-value is 0.0385. How does that relate to the threshold or the alpha that the manager has chosen?
It's the same typo.
That is less than the alpha of 0.1. And what do we do when the p-value is low?
Reject it.
We are going to reject this null hypothesis because there is convincing evidence that P is less than the 63%. Again, that is the alternative hypothesis. We have convincing evidence that this person has made a difference. Good for them. It was 63%, wasn't it? Okay. All right. Oh, but I don't know. Okay.
Literally, like, you can see a difference in numbers, so like, why do you have to do all that?
Well, because sometimes it's not that obvious. That's why. All right, now back to part B, our errors here. A type 1 error. This is, we say, yeah, we say we have convincing evidence that P is less than 0.63, but it really is not. What's the consequence here? Gentlemen, what's the consequence here? If we say that the true proportion that have to wait longer than 2 minutes is less than 0.63, are we going to keep that new employee?
No.
If we say that the true proportion is less now, wouldn't we keep that person? Shows that they made a big difference, right? But it's really not lower. So they really didn't make a difference. So what are we going to do with this employee? Are we going to keep him?
Fire.
Yeah, we're going to keep this person, but we shouldn't. We should not have. We're going to keep an unnecessary employee. A type 2 error. This is, we say, we do not have convincing evidence that P is less than 0.63, but it really is. What's going to happen to that employee in this situation? Yeah, we're going to fire a good employee. And guess what? Our drive-through times are going to still be just as bad as they've always been, even though this person helped them make a difference.